Yes, it is. There we go. Well, this should be interesting. The surveys basically said that most people were happy that the videos were there, but a lot of people said, there's this crazy glare, and it's true. If you put your head right there during the day, you see a glare go right through there. So all day I've been refining this idea, and this is the fourth class I've played with it. But I think we got it sussed out. So this should be fun. Yeah. Yeah, magnet. I put a magnet on the end of the yardstick.
Duct tape the magnet.
Just duct tape the magnet. I like to duct tape magnets to things. It's fun. It's fun to duct tape magnets to things. So anyway, yeah, I have lots of magnets that have been duct taped to things.
You have a lot of duct tape?
Yeah. They come in rolls. You can get a whole roll of duct tape for like $4. It's pretty great.
Wow.
Okay, so we'll see how this works. Ladies and gentlemen, last unit, there will be a quiz on quantum. It's a lot of fun. Quantum's really neat. And there is a lot of overlap. Guys, there is a lot of overlap with a unit you learned in chemistry. When you learned about electron configurations in chemistry, you learned a little bit about quantum. Now you're going to learn a little bit more. So we're going to start with reviewing quantum, then we're going to switch it over to physics. We're going to start reviewing, talking about the atom. Now there was this guy named Rutherford, and 100 years ago or so, or more than 100, about 150 years ago, he put all the electrons in an atom where? On the outside, the big shell, right? So there was Dalton and Thomson and Rutherford, and so basically Rutherford put all the atoms in one big shell, which was great. So as far as Rutherford was concerned, there's a proton over here, and then there was a shell. Now, Bohr's student, Rutherford's student. Bohr took the single shell and he did what? He expanded it to multiple shells. So we have multiple shells called energy levels. Okay? So we're going to pretend this one is level 1, this one's level 2, and this one's level 3. So far, so good? All right. So electrons exist. We're going to focus on a single electron. We're just going to pretend it's a hydrogen atom, and it's got one electron. It's got one electron right there in level 1. So far, so good? Now, we're going to say this level 1 is at 1 unit of energy. This is 1 unit of energy at level 1. What's the level, how many units of energy is level 2? 2? Let's make it a little bit more than 2. 10? 10, okay. So level 2 is 10 units of energy. Okay? And if there was a third level, how big is level 3? 100? Okay, 100. All right. This will make fun for fun mental math. All right, so level 3 is 100 units of energy. This is all sorts of fun. Period 4 did like 1, 4, and 9. I can do that in my head. But okay. So if you have an electron sitting at level 1, it's at what's called the ground state. If you give atoms if you give atoms energy, those electrons will jump up. And they will jump up to discrete levels. Those discrete amount of energy that they need, those discrete levels, are called quantum. A single quantum. Multiple quantums are a quanta. So if you have one piece of information, it's called a datum. If you have lots of them, it's data. If you have one packet of energy, it's called a quantum. If you have a whole bunch, it's called a quanta. So far, so good? Okay, so you should have learned this round about October, November of last year in chemistry, or last year in chemistry. It was basic chemistry. Electrons are spinning around, and they're in energy levels. And quantum, anytime you hear about quantum, what they're referring to is electrons that have a discrete amount of energy. So, in energy shells. One of the things we're going to be talking about next week, maybe Friday, we'll see, is how energy can manifest itself as a wave or a particle. Things that we usually think of like particles, like an electron, it's a particle. There it is. And electrons can act like waves. And light, which we usually think of as a wave, can actually act like a particle. It's crazy. But that's quantum physics. Okay, we're going to talk about this in a little bit. This will be very, very important. So let's do a quick review of our part of quantum mechanics, and that is light. So we remember that all electromagnetic radiation is waves of various frequencies and wavelengths, from really, really long wavelength radio wave and really, really short wavelength gamma rays, but they're all electromagnetic radiation. The light you see has a lot in common with the cell phone radiation that's coming out of the cell phone radio waves. And the important thing to remember is they all move at the same speed. They all move at 3 times 10 to the 8th meters per second, which we call c. Is this familiar? This is like, okay, I remember doing this back in like light and color. C. C. It's a C. Yo, Carol, C. Okay, so c is a velocity, meters per second, and that's equivalent to, or equal to, a wavelength times a frequency. Now, wavelength is lambda. What is the unit for wavelength? Meters. Frequency is how often you get something, how many waves you get per second. What's the unit for frequency? Hertz. And by hertz, hertz is just a named unit for a what? A per second. So we have meters per second. So when you multiply a wave's wavelength by a wave's frequency, you get a wave speed. And because they're all moving at the same speed, and we usually just assume it's c in air, if you know the wavelength, then you know the frequency. You just divide the wavelength into c, you get frequency. Divide the frequency into c, and you get wavelength. It's very, very easy. Okay? Look familiar? You were tested on this about 2 months ago? Cool. Okay. This is new. This idea is new. And that idea is, because of this guy, maybe because of him, we named this after him. We named it after Maxwell Planck. We can take the frequency and realize that frequency and energy vary with each other. The higher your frequency, the more energy you have. No one ever got turned into the Hulk by absorbing radio waves. But gamma rays, those have a lot of energy. And nobody ever worries about getting too many radio waves or microwaves, but X-rays, that could harm you. Okay? So the high frequency waves have more energy. And we're going to investigate this idea in a little bit. Okay, questions? Okay, so remind ourselves Bohr's quantum model. Bohr said the electrons exist in energy levels. They can be in level 1, level 2, level 3. They can't be anywhere in between. They will instantaneously move from level 1 to level 2, but they can't be anywhere in between. They can jump from one level to another level, but that's it. So, and again, quantum science is the idea or the study of these discrete packets of energy. You know what I mean by discrete? Okay, when someone says be discrete, what do they usually mean? Yeah, keep it to yourself, right? Don't go flapping it out. You're like, ah! Make sure when you say be discrete, you mean keep it to a very small number of people, a very specific number of people. Like my gossip club, I'm only going to tell my gossip club. There are 4 people. I'm only going to tell 4 people. In science, discrete means a very specific number. So discrete means a very specific number. So if I say this car costs $10,000, it costs $10,000. It doesn't cost $95,918. That's not discrete. Okay, so here we have an electron hanging out at level 1. This is what we call the ground state. Electrons exist in their ground state. He's like, I'm low energy electron. I'm in my ground state. Many of you, your ground state is in front of the television and a lazy boy at 6 o'clock at night. If I give this electron some energy, I can force it to become excited. I can get it into a higher level. That's an excited state. How much energy must I give that electron to get it to level 2? 10 minus 1, so 9. So if I give that electron 9 units of energy, it's going to come up here. If I give it plus 9 units of energy, it's going to jump to level 2. It is now what we call excited. It's now in an excited state. It's excited. It's like, I was a ground state, and then someone gave me $9. That's very exciting. I'm going up. So it jumps up. It's there instantly. Doesn't spend a lot of time there. In fact, at the moment it jumps up, it realizes it's at a high energy system, and it jumps back down. So it jumps back down here. And what does it do with that 9 units of energy? It gives it off, exactly. It loses 9 units of energy. So what happens is a photon comes in, strikes the electron, drives it up to level 2. When the electron comes back down, it drops that 9 energy in the form of another photon. Or something else. And here's the beauty of quantum science. Maybe that 9 units came from heat. Maybe it came from electricity. Maybe it came from light. Maybe it came from magnetism. All sorts of different types of energy can be mixed together in the quantum state. It doesn't matter what goes in and what comes out, as long as the amount of energy going in and coming out are the same. Does that idea make sense? How does a light bulb make light? Electricity goes in, light comes out. This is basically the same idea. Okay, now here's the important thing about quantum. Okay, give me a thumbs up if you're with me so far. Some of you are good, some of you are bored, some of you are like, I don't really care. Okay, so if it takes 9 units to go up, it's going to take 9 units to come back down. If I give this electron in the ground state 4 units of energy, what happens? Nothing. Exactly. Some of you remember your quantum. Nothing. If I give it 5, what happens? Nothing. If I give it 8, what happens? Nothing. If you give it 9, it jumps up. What if I give it 10? It still only jumps up 1, and that extra unit of energy is lost. It just goes right through the atom. It takes the 9 at once, and the rest just allows it to pass by. What if I give it 45? It jumps up 1, and the remainder 36 just travels right by. Make sense? What if I give it 99? It's going to jump up 2 levels. If I give it, I'm going to use a different color. I should have used red to begin with, and then green, but oh well. Sorry about this. This is backwards. If I give it 99, it's going to jump way up here. Hey, I'm super excited. I went from 1 to 3 in a 99 jump. At which point, it has options. It can jump back down to level 2, and then to level 1, or it can jump down to level 1 in one shot. And again, the amount of energy is irrelevant. The type of energy is irrelevant. The amount is all that matters. The amount should be the same. If I give it 99, it's going to come back with 99. Make sense? That's the basic idea. Photons or something comes in, causes an electron to jump up to an excited state. It doesn't stay there for very long. In fact, in an infinitesimally small amount of time, it is allowed to come back down to the ground state, and in order to come back down to the ground state, it has to give off its photon. Now we can take advantage of this. We can pump high voltage into gas and make that gas glow, and then put it in a tube and make it say, open, bzz, 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 open, 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 come buy my tacos, bzz, bzz, bzz. That's how neon signs work. We send electricity in, we get light out. Is that the only place we use a phenomenon like that? Can you think of a system where light goes in and electricity comes out? Solar panels. You're going to use these in the lab. These are my tiny little solar panels. The cute little solar panels. The solar panels, light goes in and electricity comes out. Now we're going to discuss how that works in a little bit. Give me a thumbs up if you're comfortable with this idea about quantum up-downness. Okay. I hesitated to put this next part in, but I got to put it in anyway because it's kind of cool. What we call this is atomic absorption. So when the atom absorbs energy, we call it atomic absorption, when a quantum jumps to the next level. So when the electron jumps from level 1 to level 2, or from level 1 to level 3, or from level 2 to level 3, that's atomic absorption. It absorbs very specific amounts of energy. It's like Goldilocks. Goldilocks. You know the story. There was a mama bear, a papa bear, and a baby bear. And the mama bear had a medium-sized bowl of porridge, and the papa bear had a big bowl of porridge, and the baby bear had a small bowl of porridge. You remember the story. So the papa bear's bowl of porridge was too big, and the baby bear's bowl of porridge was too small. So what did Goldilocks eat? The one that was just right. Okay. I'm changing it for my purposes, but the idea is it's just right. So here's kind of an interesting idea. If we look at starlight, billions and billions of miles away, and we look at it through a prism, and we notice there are certain bands of light that are missing, we know that that light had to have passed through certain gases that only absorb that band of light. Make sense? It's kind of like, here's another analogy. If you had everybody's helmets lined up in the football team, and you came in and said, I wonder who's practicing right now. Number 4, number 5, oh, number 7's helmet's missing. Number 8, number 9, number 12's helmet's missing. Then you would know number 12 and number 7 are practicing. Make sense? That's how we know what certain planets are made out of. Because the light that comes through gets absorbed at very specific wavelengths. And we're like, there should be a blue line right there. There's not a blue line right there. That means that planet probably is made of a whole bunch of this. That's atomic absorption. That's how we know. Atomic emission is the exact opposite, where what we do is we heat up the gas, we run some high voltage through a little tube of neon, and the colors that come out are indicative of whatever material that thing is made out of. Neon signs are red, you might have noticed. But you know what other color neon signs are? Green, blue, yeah. Because neon emits red band light and blue bands and green bands. It emits lots of different light. So all you do if you want to get a green light out of neon is you coat the inside of the outside of the tube with something that absorbs red light. Red light gets absorbed, the green light gets emitted. But usually, if you don't coat the screen at all, the red light from the neon is a lot brighter, so you usually see neon as red. But if you want to get different colors, that's okay. You just coat the inside of the tube. Yeah.
What about when it's like a white neon sign? Oh, wait, just kidding. Never mind. It's your question. Okay, never mind.
All right.
Never mind.
So I love this. I love this animation. I stole this from the internet. I didn't even cite it. I thought this was so cool. So the little blue photon? He's like bounce, 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 bounce. The little blue photon has a very high frequency, but a very small wavelength. And then the big lumbering red photon has a very big wavelength, but a very slow frequency. Kind of cool. But you'll notice they're all moving at the same speed. So the blue, the green, the orange, and the red are all moving at the same speed. The blue one's going bounce, 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 high frequency, low wavelength. The red one's going bounce, bounce, long wavelength, low frequency. Okay. And if you can't see this, I apologize. This is totally arbitrary. The idea is the bigger the gap in energy, the more towards the bluish end of the frequency wavelength you're going to get. So red would be a small gap. So this is why I said this is backwards. A gap between 1 and 10, only 9 units of energy would probably be red, or a gap between 10 and 100 would probably be blue if it has more energy. Does that idea make sense? Sorry, I didn't really think that ahead, but yeah, more energy tends to be reddish. High energy tends to be bluish or purplish. And we're going to investigate that in lab. In fact, I ordered these. It turns out you can get about 50 LEDs for like $12. Remember these little LED guys? So I did. Thank you, Amazon. And I got a red LED and a green LED and a blue LED. RGB. And they're pretty neat. They're all powered by the same battery. But compare the energies of each photon coming out. Which of these lights has higher energy photons coming out? the blue. Each photon leaving the blue light has more energy than each photon leaving the green light. And the green light, each photon leaving the green light, has more energy than each photon leaving the red light. Does that idea make sense? So you're going to investigate this tomorrow. You're going to prove it, or maybe tomorrow. I haven't really decided when I want to do the lab. We do it tomorrow. We might do videos tomorrow and lab on Tuesday. That's kind of where I'm leaning. Videos tomorrow and lab on Tuesday? Yeah. And the yearbook party's tomorrow too, so. Yep. Neither do I, but yeah, it's at 1 o'clock tomorrow. All right, so most of us will. I mean, it's like 10 minutes, the last 10 minutes of class. 6 periods totally hosed, but you know, whatever you do. Okay, so, yeah. I'm sorry? 6 periods of my prep, so it doesn't look like me at all. But if you have 6-period English, you're like, no English. No student aid. Yeah, a lot of your student aids. Okay, so once again, quick review. If you know a wave's frequency, you know its wavelength. Wavelength varies inversely with frequency. Energy varies with frequency, so energy varies inversely with wavelength. And there's that formula of it again that I'm going to show you. Max Planck. There he is. There's Max. Max is like, I want to think about quantum. Me and Einstein, we're like bros. So we have a number for him. A number that turns each individual photon into a packet of joules. Each individual energy into a packet of joules, and it is 6.6 times 10 to the negative 34 joule seconds. It allows you to take the frequency of a photon, multiply it by Planck's constant. That tells you how much energy each of those photons is carrying. Good old Planck's constant. 6.6 times 10 to the negative 34 joule seconds. You could, and there's actually a way, and my mentor showed me how to do it, but I'm not going to do it. You can actually find out how much actual energy, what the actual quantum of each of these photons are. Experimentally. I like to use lasers. Lasers are easier, but lights work too. That's what it means. So if you have something that has a higher frequency, blue and green light, it's going to carry more energy per photon. Now realize, this is 10 to the negative 34. A joule is actually a really big unit. Remember, a joule, 1 joule is the amount of energy required to raise 1 Newton of something 1 meter. 1 meter. It's a lot of energy. So photons, we're talking about, you need lots and lots of photons to make it to a joule. That was for DJ. Make sure everybody's awake. Do something interesting. Sorry, I don't have anything really cool. The lab is really neat. Oh, I do have something cool. This thing. This is a 3-year-old bottle of tonic water. I take that back. This is a 6-year-old bottle of tonic water. Tonic water has a chemical called quinine in it. I guess people put like liquor in it and then drink it, but I needed it for one purpose, and this is the purpose I needed it for. Oh, I have to mention this. Taking it apart, because the crystal is broken. But if you actually, this is one of the green lasers. You can see a little green dot. If you look inside the green laser, you know what you see? A red laser. I never knew this. I actually learned this. So it uses a red laser to cause the light to be ejected. It's called a pumping laser. It uses the green laser to excite the molecule, so they emit green light. It's kind of neat. So it's cheaper to make it. You can't see it on the wall. It's really, really dim. It uses a red or an infrared laser because it's cheap to make. And then that infrared laser, basically kind of like a transformer, steps up voltage and steps down current. So that red laser steps up frequency until it gets to a green light. It's kind of cool. So here I got my blue laser, got my green laser. Okay, so look what happens when the green laser goes through the tonic water. You can kind of see it in there, but not all that much. Look what happens when the purple laser goes through the tonic water. And the cool thing is, what color is the beam? You can't see it? Can you see it now?
No, that's green.
With the stripes, right, okay. So here, let me just bring it over. So, here. Do you see it now? Yeah. So this is a purple laser. Here, I'll show you. There you go. Purple laser. It's a purple laser that makes a blue light in the tonic water. Isn't that neat? This is called fluorescence, where we're basically exciting the atoms, but they're not able to actually send purple light out. So they do their best job, and they send out green light, and the rest of the light just travels through. So you can still see the purple light. The purple light still shows up. It's not able to absorb all the energy. But the energy that is absorbed is causing the atoms in the quinine to jump up and jump down and send out blue light. The green light doesn't have enough energy to cause the atoms to be excited. So the green light just goes right through the material. No excitation. The purple light, or the violet light, the atoms get excited. I thought that was pretty cool. So anyway, there we go. Oh, if you're curious, I just put a slide on here because it's kind of fun. This is what hydrogen looks like. There's a stripe there, a stripe here, and then you can't see the red; it gets mixed up. These are all the stripes of various materials. Okay, this is where we're going to spend most of our time: the photoelectric effect. Someone noticed something kind of cool when we were using electroscopes. No one in this room, because we didn't have the equipment. But remember the electroscope? The electroscope had a ball, and then that ball was attached to leaves, and then the whole thing was put in a flask. Remember the electroscopes? And when you brought a negatively charged rod to the electroscope, the positives went up, the negatives went down, and the leaves separated. Starting to look familiar? Okay, someone noticed something kind of interesting. It turned out, if you took an electroscope outside, and if the ball was really big, or there was a plate, you took it outside, the leaves would move out. If you took the electroscope outside, it turns out the leaves would move out. But only during the daytime, never at night. Why? The sun, obviously. What was the sun doing? Yeah. The sun was lighting this up. And it wasn't a heat issue. What was happening is electrons were being ejected from the material and sent down the leaves. This is called the photoelectric effect. The exact same thing that happens with these. So, this is what happens. Going back to our atom, you gave me the atom 1, 10, and 100. Nice logarithmic scale there. If I give my electron 1 unit of energy, nothing happens. 2, nothing. Give it 9, it ends up over here. Give it 99, it ends up over here. But what happens if I give it 109? Something interesting happens. When the electron runs out of shells, this is what it does. Oh, level 1. Hanging out. Oh, I'm going to go level 2? Okay, I'll go to level 2. Go to level 2. Oh, level 3? Okay, level 3. Oh, more energy. There's no more levels. So what does it do? It gets ejected. It gets ejected out of the atom, and it becomes what's known as a high energy electron. That electron actually has energy. It works like this. If I give it 99, it goes pew, pop. If I give it 109, it goes zing. High energy electron gets launched out. It takes all that excess energy and it carries with it in a certain way, like kind of like this. Solar cell. Here's my solar cell. Photon comes in. How much energy does the photon carry? 7 units of energy. Unit is carrying 7 units of energy, but the material that it strikes keeps a little energy to itself. So it's the energy it takes for the electron to go from here out to level 3. It keeps a little bit of energy. That little bit of energy is called a work function, and it's given the letter phi. I'm sorry it's phi, but it is. And it is the work function. What's the work function of my material? 5. The work function of my material is 5 units of energy. So the photon comes in with 7, the atom keeps 5, and what comes out is a high energy electron of how much energy? 2 units. Okay? It comes out with 2 units. Well, the goal is make material with a work function as low as possible, or make a device that runs on as low voltage as possible. So if my calculator is the device, this is a solar cell on my calculator, light comes in at 7, the calculator can only use 2 because the work function of the solar cell keeps 5 to itself. Does that idea make sense? Okay. So this is the formula. Energy comes in, has a certain amount of energy. We're going to give it a new name here in a second. Energy comes in, the wave comes in with a certain amount of energy. The atom keeps a little bit to itself. It's the energy tax. Keeps a little bit to itself, and then whatever's left over gets translated into the electron as a high energy electron. This is the formula. HF is the energy that's coming in, the wavelet's coming in. Phi is the work function, and Ke is the amount of energy each of those electrons has. Yes?
What does it do with the rotation?
I don't know. It doesn't necessarily warm up, so I don't know. The question was, what does the atom do with the work function energy? I don't know. I'll look into it, and if you remember, you can ask me later. We'll take a look. You can probably figure it out too. There's tons of stuff on YouTube about the photoelectric effect because this is huge. If you want to make a lot of money, come up with materials that have an extremely low work function. Right now, solar cells only work during the daytime because you need visible light or ultraviolet. But if you can come up with a solar cell whose work function is below the infrared, it will work all the time because everything's emitting infrared. So, and you wouldn't even have to put it out somewhere. You could just like put it underground and it would still work because everything emits infrared. Okay, so breaking down again. Yeah. Have fun. Good luck. Run fast, hit hard. Okay, so that's the holy grail. We want to get our work function as low as possible so we can harvest as much of the energy as possible as actually useful work. For instance, let's take DJ's 5 work function material and let's replace it with something that only has 1 unit of energy. Then the electrons that are coming out have a full, how much? 6 units of energy. So you can power something else, something more powerful. Does that idea make sense? Now, we have to come up with a new unit. If you remember from your electrostatics, you had a formula that looked like this. U equal QV. Energy of an electron equaled coulombs times volts. So 1 joule was 1 coulomb times 1 volt. Remember that a little bit? You don't? Pretend you did. So a coulomb is a big unit. You know what's a really small unit? An E. An electron has 1.6 times 10 to the negative 19 negative coulombs of charge. It's a small unit, but it is a fundamental unit. So what if we replace the coulomb with an E? This is what happens. 1 E times 1 volt is 1 E volt. An E volt. It's called an electron volt. And it's a really handy unit, and I'll tell you why. It is the energy 1 electron has when it goes through 1 volt. If an electron is carrying 3 EVs of energy, guess how much voltage comes out of the solar cell? 3 volts. if an electron is carrying 4 EVs, guess how much voltage comes out of the solar cell? 4 volts. It's a really handy unit. So what we do is we convert our wave energy to EV. If a wave comes in carrying 7 EVs, and the work function is only 1 EV, then 6 EVs of energy comes out per electron. Why is that important? Because that means you can, because remember, we're blasting with billions upon billions of photons and getting billions and billions of electrons out. So this means you can power a device up to 6 volts. Calculators, 1.5 volts. Okay, this is kind of cool. I took these little solar cells. These came in a kit that were just given to me. Tiny little solar cells. They say 0.45 volts. I plugged them into our multimeter, which you love so much. I hope it's going to work. Somebody broke the multimeter off in the thing. Let's see if it's going to work. Okay. Oh, I have to hold it in apparently. I'm still working on fixing it. Right now, this solar cell is only picking up 14.3 millivolts. Let me illuminate it a little bit. Ooh, 65 millivolts. Hey. Yeah, this is not a very bright laser. But what would happen if I took it up here and I brought it up into something white? Here we go. Now we're getting, oh yeah, 103 millivolts. Okay. So basically, this is how this works. Photons come in, the atom keeps a little energy. I don't know what it does with it. And whatever comes out, the difference, that's a high energy electron. If you understand this idea, I have a question for you. Take the solar cell. Let's say, make it really easy, let's say it makes 1 volt in daylight. Then, like in the morning, 1 volt, just normal daylight from the sun. Then at high noon, you have twice as much light. Same type of light, but twice as much. Will you get more than 1 volt, less than 1 volt, or still the same 1 volt? Talk with your neighbor. Take a minute or two and decide the same type of light, but more of it. Will you get more than 1 volt, less than 1 volt, or the same 1 volt? Okay. You've had some time to talk about it. Manufacturing defect. Okay. So you got the solar cell. It gets you 1 volt. Then you take that same solar cell and you put it up at high noon. Same type of light. Still coming from the sun, but more of it. Who says you get more than 1 volt? 1, 2, 3, 4. Who says you get less than 1 volt? Nobody. Who says you get the same volt? And you'd be right. If it's the same type of light, you're going to get the same voltage. What you will get more of is what? Current, exactly. Remember, current is the flow of electrons. More photons means more electrons. More photons hitting the material means more electrons out, and current is electrons per time. Make sense? Okay. Now, same scenario. Only this time, you're going to take the solar cell, and you're going to go from, let's make it really easy. You put a filter over the top of it. Only green light can hit it. Then you take the filter away, and all wavelengths of light can hit it. More voltage or less? More voltage. Because now, not only are you going to get the green photons that are going to excite it, you're also going to get the blue, the violet, and the ultraviolet photons that are going to excite it. So when you get higher energy photons, then you get more voltage. Which is why I said the holy grail for solar cells is to get this work function so low that even even infrared will cause electrons to be ejected. Then you just put them into a transformer, and you're good to go. Okay, last thing. Good, great timing. Last thing, the threshold frequency is the lowest frequency photon that will cause an electron to be ejected. In other words, even in our example here, the threshold wavelength or the threshold frequency is the photon that's carrying 99 units of energy. At 99, that's the point at which electrons can be ejected. So 99 and up, that is the threshold. 99 is the threshold. If you get them carrying 100, electron gets ejected. If it's only carrying 98, no electrons get ejected. That is the threshold frequency or the threshold wavelength. Okay. Questions? Is your brain burning yet?
It's smoky.
Yeah, a little. Is there smoke? There's no fire yet, but there's smoke. Okay, cool. So we'll call it a day there. See how this works.